Today you're watching a video on exponents, something you're already probably familiar with, but making sure you understand some of the newer concepts that we are introducing. So let's just go over exponents. Exponents are used to represent repeated multiplication, which means multiplying the same factor or number over and over again. So for example, we have 3 to the 5th power. What this is saying is 3 times 3 times 3 times 3 times 3. You should already know 3 is called the base. It's the number that's being multiplied repeatedly, and you better know that 5 is the exponent. How many times you're multiplying the base together. Exponents have rules. I strongly suggest you documenting these rules by creating a foldable or putting them in your notebook. However, you must know these rules to be successful. Let's begin. Same base rule. Same base rule is when multiplying powers that have the same base, you keep the base and add the exponent. So here's an example. A to the m power times a to the n power equals, keep the base a, keep the base a, and add the exponents. Same thing here with numbers. 5 to the 6 times 5 to the 3rd equals 5 to the 6 plus 3, or 5 to the 9th. Because these numbers are large, you don't have to do 5 times 5 times 5 9 times. This is your final answer, simplified. I do not need a numerical value, no. So, given what we just talked about, please try these two examples. Again, you could create a foldable and document these with your foldable. If you need to see an example of a foldable, please check with your teacher, as we've already created one. Example 1, a to the 5th times a to the 13th. Same base rule, keep the base. How do I know they're the same? Because they both are a. Keep the base, add the exponents, a to the 13th power. Oh goodness, example 2 is looking a little tricky, but it's not. I notice that I have bases here that are the same and bases here that are the same. And it kind of puts me in the mind of combining like terms. So, same base, multiplication, add the exponents. Same base for the b's again, multiplication, add the exponents. And you should get 5 to the 5th, b to the 6th. You could have a multiplication signs, but not necessary. As we are getting older, we don't need to represent every single thing. We know when different variables and numbers are side by side, multiplication is the operation. Let's continue. Different base rule. When multiplying powers that have different bases and the same exponents, you multiply the bases and keep the exponent. Let's look at the example. A to the m times b to the m is nothing more than a times b to the m power. Multiply the bases, keep the exponent. Same thing here, 3 squared times 4 squared equals 3 times 4 squared, which equals 12 squared, which equals 144. The reason you can simplify this one is because they're numbers. And if it was a larger number like 12 to the 6th, I would just leave it as 12 to the 6th. However, 12 squared, we know 144, perfect square, we can simplify that. Here are two examples for the new rule, different base. They're different bases, but the same exponent. So keep the exponent, multiply the bases. Same thing here. Keep the exponent, multiply the bases, and that can be simplified, and I'm just going to leave it as a squared. I am not going to take out my calculator or do the math in my head, definitely not, or write it down. 8 to the 3rd power. What about power rule? We're on example 3. When raising a power to a power, keep the base and multiply the exponents. So here are 3 examples. A squared to the 3rd power, keep the base and multiply the exponents, and you get a to the 6th power. 3 squared to the 3rd power, 3 times 2 is 6. 3 to the 6th power, which equals 729. AM to the n power equals AM times n. Again, this is multiplication, and you can have it like that, but we are getting older. We know 2 variables side by side, the operation is multiplication. Continuing on, here are 2 more examples. Keep the base, multiply the exponent, because it's the power rule. These are raised to a power. Last one here on kind of multiplication, then we'll look at a different direction. Expanded power rule. When raising a product to a power, that means 2 things in parentheses being multiplied together. Product to a power, distribute to each base. So AB to the m power, I'm distributing to each base. And what operation is taking place between the A and B? Multiplication, so that's why I have it there. The same thing with 4x cubed, all to the 2nd power. I distribute that 2 to everything. Oh my goodness, there's no exponent with the 4. Yes, it is. We know it's a 1 there by itself. Just like if you had a variable x here, we know it's 1x or just x, and it's to the 1st power. Same thing. So 1 with the 4, 2 times 1 is 2. X third, 3 times 2 is 6. So we simplify and get 4 squared, which is 16, x to the 6th power. Let's try these. Distribute, and I get 2 to the 3rd times a to the 3rd. Again, distribute, I get 6 squared times x to the 6th, or 36 x to the 6th power. Again, you should be documenting these different rules for exponents. Let's take a look at another set of rules, continuing on. And all of these can fit in your foldable. And again, if you need a foldable example, please see your teacher. So, continuing on. Think about this question here. If when multiplying powers you add the exponents, hypothesize what you would do when dividing exponents. Take a moment, think about that. When we're multiplying exponents with the same base, we add exponents. So what are you going to do if we're dividing powers? Let's take a look and see. Quotient of power rule. When dividing powers that have the same base, you subtract, maybe you thought that, subtract the exponent of the denominator from the exponent of the numerator. So here's our example. A to the m power divided by a to the n equals m minus n. And let's think about that mathematically. Why are you subtracting? Because this is a division sign. Think about an equation when you have, I don't know, x plus 2 equals 3, and you do opposite. Because of this equal sign, it separates it, so you do opposite. The same thing is true for this division sign. Same thing is true. When we move it up, this positive n now becomes negative, and so we're subtracting. That is all we're doing. Let's look at another one. Some examples. A to the 13th over a to the 3rd. Same base, because they're both a's. What's the rule? To subtract. And now you get a to the 10th power. Continuing on, they're both same basis. 7 to the 8th power divided by 7 to the 6th power is 7 squared, or 49. Let's continue. Negative rule number 1. When the exponent is raised to a negative power, flip it and change the sign to positive. So right now we have a to the negative n power. What number is in front of that a? Right, a 1. Anything by itself is a 1. So we don't want it to be negative. Usually with exponents, the rule or definition or example or directions, I think is what I'm really looking for. The directions would say to have positive exponents because in math, we prefer positive numbers. So right now you have 1a to the m power that is negative. We want to move it down. But keep in mind, we really know a to the negative m has a 1 in front and a 1 in the denominator. If we bring it down, what happens to that sign? It now becomes positive. And you can't just bring the m down. The m is attached with the a. So you bring the a with it, make the m positive, and that 1 stays in the numerator. Here's an example with numbers. 4 to the negative 2. Well, 4 doesn't have a 1 in front, but if we move it down, it leaves the 1 or creates a 1 because something has to be in the numerator. And then the 2 becomes positive, which equals 1 over 16. Let's try these couple of examples. Take a moment if you want to pause the video and try yourself and see if you get what I get. I'm going to move it down. That means I'm crossing over that imaginary division sign, 1 in front, and my y now becomes positive. So y to the positive 7. Same thing here. Bring it down. The 2 goes with the 7. It's part of it. So I'm left with 1 7 squared, which is 1 over 49. Continuing on. Negative rule number 2. When the exponent is raised to a negative power in the denominator, flip it and change the sign to positive. So this works the same way if you have a negative in the denominator. We don't like negative exponents. It's negative in the denominator. So where can we move it to make it positive? To the numerator. It's crossing the division sign, so the sign changes to a to the positive m power. Same thing here. Move that negative 5 up. The 1 goes away because, or it's not good, it doesn't go away, it's just not there because we don't really write 1x to the 5th, we just write x to the 5th. Try these examples, pause the video, come back and take a look to see if you get what I get. All right, so example 5, bring that up. The line makes it become positive, x to the 5th. Same thing here, equals 2 to the positive 4. This rule is very simple. Zero exponent rule, anything raised to the 0 power is 1, except 0, and don't you worry about that. Anything to the 0 power except 0 is 1. Doesn't matter how big or small the number is. 8 to the 0 power, 1. Negative 9x to the 0 power, 1. Right? Think about it. Is that 1? Well, the numerator, or excuse me, 9x becomes 1, but the negative's on the outside. So the answer would be, in this case, negative 1. Please refer to a foldable given by your teacher if you need the example, but please make sure you have these different exponent rules. You'll practice and hopefully ask questions if you need help. Thanks for watching.